Okay, hello everybody, good afternoon. My name is Tamas Ban. I am working at ARM. I am working in the last year in a TFM project. My focus area was the trusted boot and the trusted firmware upgrade. Today I will give you a presentation about what we did in last year on this field. Okay, this is the short agenda of my presentation today. At the beginning there will be a few introduction slides about what is trusted environment, what is secure boot, what its responsibility, how does it work, what the basics. Then I will talk about which bootloader we are using in the TFM project. We will go into details, how does it work, why is it secure, which crypto libraries does it use, and so on. Then there will be a slide about how the firmware upgrade happens in the IoT devices, or how should it happen. There will be some alternative solutions to do the image upgrade on the device itself, and there will be some other alternative solution. What can you do with the crypto if it is too heavyweight for your device? At the end there will be a Q&A session, but please feel free to interrupt me anytime. I can answer questions during my presentation. Okay, so first of all, some introduction. What is a trusted environment? When we say something is trusted, what does it really mean? If you have a device maker, then probably or definitely you store some data on your device and not only the code. These data can be valuable for you. It can have several reasons why it's valuable. It can be sensitive user data, it can be certificates or crypto keys, or even itself, the code itself can be valuable for you because you don't want that compatible access to your code and reverse engineer it. If you lose your data, then you lose money or lose a reputation. Both of ours is not a good scenario for your company. So you want a way that you want to ensure that a malicious actor cannot access your data, cannot expose it from your device. And this is the main goal of a trusted environment. Trusted environment is something which is a combination of boot, secure boot, some hardware capabilities, and secure runtime firmware. If you have all these details together and working fine, that you can be sure that your secrets will be kept in secret in the device. If any one of these fails, for example, boot or hardware is not capable to do something, that probably you have a security hole in your system which can be exploited and your data can be extracted from the system. PSA, Platform Security Architecture, are addressing these aspects of the trusted environment one by one and give some recommendations how you implement something in order to achieve a trusted environment. In this presentation, I will more focus on the trusted boot. Okay, what is trusted boot, why we need it, and how does it work? Bootloader is a piece of code which just executed as soon as the CPU is released from the reset. This is the first line of code which runs on the device. It has many goals, like hardware initialization, but in a trusted environment, the main goal is to verify the integrity and authenticity of the other software components which are going to be run later on the system. As soon as the bootloader done with this authentication, it passes the execution for the other software and never returns. Why we need it? Because we want that only authenticated software run on the device, which is trusted and won't extract our data for somebody who has no rights to access it. How can it achieve this goal? this goal is achievable that you have a trusted anchor in the device. Trusted anchor means immutable code, immutable data. Immutable code is the bootloader itself. Then building your architecture, the base of this immutable data, you can use certain crypto algorithm to ensure that only authenticated code will run on your system, and its integrity is also correct. Okay, this bootloader design is not a new thing. There are many bootloaders on the field. A-class devices has actually several bootloaders during the boot process. But the M-class devices are different compared to the A-class devices. This is a comparison about what are the device constraints in the M-class devices. This is on the right side. And on the left side, you have seen some high-level requirement towards the bootloader. What capability should it have? The main constraints are that the code usually stored in the internal on-chip flash, and its size is limited. In most cases, the size is less than 1 megabyte. So you need all the code, the application, the bootloader must fit this 1 megabyte. The RAM, which is used for the data, it's even smaller, 256 kilobyte. It's quite a maximum in most cases. It might have some cryptographic accelerator hardware in your system, but you might don't have. So in some cases, everything must be solved in a crypto library. In other cases, there can be some coprocessor. The computing power is lower than the A-class devices. The clock rate is lower. There is no instruction cache, or there is no data cache, or in the most cases. And the pipeline is simpler compared to the A-class devices. And of course, can happen such a situation when your battery is drained and there is a power failure in the middle of some important operation. You need to be prepared for this situation. On the left, there are the high-level requirements. You need to support software upgrade because this is one of the most important aspects to be secure. If you have security vulnerability in your software, you can fix it, but without software upgrade, you cannot deploy on your device. You need probably support chain of trust to ensure that only authenticated code run on your system. And for this reason, you need a lot of cryptographic algorithms. These cryptographic algorithms usually align with the A-class devices. So on one side, there are the high-level requirement, which is quite similar to the A-class devices, and on the other side, you have the device constraint, so you have some more simpler device. These facts leads to that we must a bootloader which address specifically the M-class devices. So it's designed to run on M-class devices. In the TFM project, we use the MCUBoot, which is an open source project governed by the Linaro, which is designed for M-class devices. It has a low memory footprint. It's running from the flash, so it's execution in place. But the main reason why we use MCUBoot, because it's a major product, it already supports all the required cryptographic algorithms, like asymmetric algorithms for the origin authentication. There is RC and elliptic curve cryptography built in, and there are the hash calculation for the integrity verification. The design is reliable in the sense that it is prepared to handle the power failure scenarios as well. Okay. Last year, and then last year, we have our first TFM release, And as part of this release, we are using MCUBoot as a bootloader. Last year, we are mainly focusing on that we must port MCUBoot to fit to the TFM project. By default, MCUBoot can compile as a RTOS application. It's supported by Zephyr, Minute, and other RTOS as well. But it means that we have dependency towards an RTOS, and we want to avoid this in the TFM project. For that reason, we created a version of MCUBoot which is OS agnostic, and this version is used in TFM. In the current implementation in TFM, we are supporting RSE as an asymmetric algorithm. We combine the build process with the MCUBoot build. So in order that MCUBoot can authenticate software, it needs to do some preparation. It needs to put some header before the binary, and we need to concatenate some other fields at the end, but I will cover it later. During the build process, there are some scripts which do this job. So at the end, when you build a TFM project, you have secure binary, the non-secure binary, you have the bootloader, and the secure and non-secure binary is prepared in a way that it can be directly downloaded to the device, and MCUBoot can verify and boot it.
So at the end, did you fork from MCUBoot, the GitHub from MCUBoot from runtime IO, or are you aligning?
Copy. It's a copy. Okay, this slide is about some basic how chain of trust booting works. On the left side, you can see the orange box, which is in an ideal world, we have an immutable bootloader and some immutable data. Data can be a hash of a cryptographic key, or can be the key itself. Because it's immutable, this is by default implicit trustable. And you can derive every other software component from this anchor. So you are using asymmetric key cryptography to ensure the origin of the other images. You built in the public key in your device. It can be done as part of the boot code, or it can be put in some other hardware components like an runtime programmable memory. It depends on the device capability. The other part of the key pair, the private key, must be kept far away from the device. It must be stored somewhere in a secure server. If you want to deploy next stage software on the device, you make sure that you use the private key to create digital signature during the build process, and you send that image to the firmware in some way. Then your immutable bootloader can use the public key to decrypt that digital signature, and if it fits, then it allows to run the new image. The new image, which can be another bootloader, the BL2, can again contain some further keys. These are again public keys. These keys are used to authenticate the software components in the next stage. And the next stage can be your secure code and your non-secure code. At the end, the secure and the non-secure code will be your runtime environment. Why we need BL1, BL2? This is not a mandatory requirement. This is just a recommendation to do it in this way. If you lose your key, or not lose your key, but somebody can get access your private key, then you lose your device, basically, because then everybody can generate an image which will be fit on the authentication, and they can deploy some arbitrary code on your device, and you don't want that. Therefore, it's a good advice that for a key pair must be used for only one purpose. The root of task probably key, it's only used to verify the BL2 image. BL1 cannot be updated because it's immutable, and probably you will update BL2 only a rare occasion on your device. But it's expected that the secure and the non-secure code will get more updates. Therefore, you will use more the public keys which are incorporated in the BL2 image. If you lose those keys, then the attacker can deploy a new secure function. But if you realize that somebody stole your... sorry.
Is there any rollback protection support in this case?
Rollback protection?
Yeah, not yet. Okay, so if you realize that somebody stole your keys, then you can update the BL2 image and you can deploy new keys on the device. And when you do that, then the attacker lose the capability to deploy arbitrary code on your device. Okay, in this figure there is two parts. At the top there is a figure which is very similar to the previous one. You have the immutable code, BL2, bootloader, secure image, non-secure image. The difference is here that here the secure image is verifying the non-secure image, but this is just a kind of implementation. On the bottom, there is the situation how the booting is currently working in the TFM project. We have no BL1 bootloader implementation at this stage. This is under discussions that do we need it, will we do it later, so we haven't decided yet. We are using MCUBoot as a BL2 bootloader, and the main difference is here, that we are not signing the secure and the non-secure image separately. Instead, we are combining the secure and the non-secure image into one big binary blob, which gets a signature together. BL2 verifies this combined binary blob, the integrity and the authenticity, and then it will start the secure code, which will do some runtime software environment initialization and then pass the execution to the non-secure. But here, here we don't need any further authentication because it is done by the bootloader at the beginning. Okay. Any question? Okay, if no, then I go on. The next few slides will be about how the MCUBoot works. Okay. On the right side, we have a memory map. This is a static memory map on the M-class devices. The bootloader at the beginning of the flash. This is because the core starts to execute code which is at the 0 memory address. After the bootloader, we have two memory partitions. We have memory partition 0 and we have memory partition 1. This is for the active image. So you can have an active image which size is smaller than even half of the flash. And this image is splitted for two parts at least. You have the secure firmware here and you have the non-secure firmware here. The code must be linked that it can run from this memory range. So it is execution in place, it is a position dependent code. I mentioned that the image must get some header and other preparation to be able to authenticate it by the bootloader. That's the reason why the header is at the beginning of the second firmware, and we have TLV timeline value fields at the end. Here are the hash value, and here are the digital signature, which is about this part, the header, the secure part, and the non-secure part. At the end of the active image, there is a trailer which is used for further purposes, but I will cover it later. Okay, so your active image is running from this memory space. You want to do an upgrade. You have an upgrade client which will download the new software, and it must place to somewhere. We have a secondary memory slot which is the equal size with the first one, and the new image will go to this place here. Okay, on the other side of the slide, you can see in high level how the MCUBoot works, how it does the upgrade. The main thing is that your new software can't run from this memory address range because it was linked to the first slot. So if you try to run it from here, it will crash immediately. So you need an operation when you swap these two memory content, and this is done by the MCUBoot. After it released from preset, it parses the memory content. In an ideal case, there was no power failure before, so we have a clear situation that we have a new image in the slot 1. This is realized by the bootloader because there is a magic value at the end of the memory partition. If it is realized that there is a new software, it starts to authenticate it. In case of successful authentication, it will do the swapping. I will have a slide later how the swapping works. After the swapping, the new image was copied to the active memory area, and actually it can be started by the MCUBoot. MCUBoot passes the execution and let the new software run. Okay, this slide is about how the swapping works. It's divided into rounds, so it means that only a small portion of the memory area is copied at once. The previous slide, there is a third memory partition which was not mentioned before. This is the scratch area. The scratch area is used as a temporary storage place during the image swapping. Okay, I have an animation here. So MCUBoot starts the swapping at the end of the memory partitions. So you can see here that in the active image area, we already have the new image, but only some part of it. The last pieces are still the old software. And the other side, it's the opposite. On the slot 1 partition, we have the old image, but there are the last bits here. Okay, so the first step is to erase the scratch, copy the slot 1 content to the scratch area, save some status information that about the progress of the swapping, erase slot 1, copy that content of slot 0 to the slot 1, again do some swap status saving, erase, copy, and it's done. It is designed to be power failure. That was the reason that during the swapping we saved some status information at the end of the active memory area. If any phase that we have a power failure, then after the power comes back, MCUBoot can recover what was the actual progress of the previous swapping, and it can finish it. It doesn't matter how many times we have the power failure during the swapping. Okay, this is a slide about how we get the new software. Because MCUBoot is not involved that download a new software from a server or download a new software through any interface. Yeah.
I have a quick question. Does the scheme do rollback if the new image failed to start?
There will be a slide after it.
Okay.
Yeah, I will answer that question that time.
Okay. One more question. In the layout of the flash partition, did you miss another partition for data? Because conceivably, you will store data and then...
No, actually, this partition is the flash. So you have a code which is the read-only code and the read-write code as well. So after the image is started, it will copy the read-write data from the ROM to the ROM.
From the previous image? You're updating, right? There's the old firmware, the new firmware, right?
Yes.
After the new image starts, the new image will copy?
No, when? Okay. So here, when your update client downloads the new image to the flash, then you have the read-only code here, and you have the read-write data here.
Yeah, but there might be persistent data.
Yeah, persistent data from the app. That's what I meant. Yes.
This is yeah.
That's a separate.
Yeah,
that's part of my
yeah,
question.
Okay. That must be a separate partition.
Got it. Okay. Just confirm.
Okay.
Thanks.
Okay. So back to the slide. Okay. So downloading the new software is not the responsibility of the MCUBoot. So you need an update client, which is part of your runtime firmware, which has the capability through some interface, wireless or wired interface, download somewhere and somehow the new software. This is, here we have a server somewhere which send a notification to the update client that, hey, we have a new firmware for you, we download the new firmware. After we got the new firmware, this must be authenticated before writing it to the flash. The reason, because it's a good idea to authenticate before writing it to the flash, because you might get some arbitrary code from somewhere else, and which can be a denial of service attack as well. The update client functionality can be split between the secure and the non-secure world. The non-secure part of the update client is responsible to downloading the software, and the secure function, secure trusted update function, is responsible to do the authentication of the downloaded new firmware image. After the authentication was done with success, we write the code to the slot 1 memory partition, which is for the new code, and then the update client can restart the whole system. After reset, the bootloader will run again, as I showed you how it realized that we have something in the slot 1. It will change the content of the slot 1 and the slot 2, and it will start the slot 0. And after that, your new code will run on the device. Okay, so there was a question about what happens if your new image will fail. Actually, it can happen. So if you have a complicated device and your test cases, the test coverage is not big enough that check every cases, that there is a probability that when you do the update, the new firmware image will crash. For that reason, there is a fallback mechanism built in the MCUBoot. But the main point is here that you need something built in self-test in your firmware, because it will be a crash, which is obvious that it doesn't work, but it can be a hidden bug in your system which only affects some part of your code. It can run, but it doesn't work as you expected. So this built-in self-test must verify the image, or at least it must verify that we have a network connectivity towards the server. If we realize that it doesn't work as expected, we can still download the new software. If this built-in test was passed, then we can mark a special field in the flash which indicates that the image was verified and now it is a persistent run mode. If for any reason this test doesn't pass, then we have the possibility to reset the device. Here we have the software upgrade. We have the old image, new image, do the reboot, we do the upgrade, and now here we are doing the test. If the test was OK, then nothing changed. We confirm in the flash that this image, OK, it's run correctly. And if we have some rollback protection in the system, then we set the rollback counter to the new value only at this stage. If the test was not OK, then we reboot the system. MCUBoot checks the special flag in the flash memory, and because it haven't been set due to the test failure, it will revert back to the old image, to the active memory partition, and it will run it again.
Yep. After that, will the new image be downloaded again? Because after swap to the old image to active image partition, right? So will the new image be downloaded from web server again? I mean, he will find the new version again, then download it and update it and reboot and do the same thing.
There was a thread covered by David exactly explaining that. So David Brown from Linaro presented a threat model which actually wears out the device by just doing that. And what he said that is very difficult problem to fix. Like he didn't have any recommendation for how that can be fixed. So that's the answer.
Okay.
What if you want to manually switch back to the old partition? Let's say you run all the tests, everything's fine, but then you figure out that one case is not covered from your tests, and you have to roll back.
Actually, this can be covered by the runtime firmware. If you have a communication channel between them, you can realize that there is a problem with your firmware, then you can activate a code which clear that special flag. You can reset the device and it can do it. Or even more, you can fix the bug and do another upgrade.
Maybe it's not that fast to fix.
Just an interesting tidbit of information that Runtime IO, the people that actually developed this code, they don't generally use this. They will deploy a system with the rollback enabled, maybe a dozen or 100 devices as kind of a beta test. And then the main deployment doesn't enable the rollback, and the devices just boot or they don't work at all. There's also risk when you do this. If the power fails at a bad time, then it does a rollback unnecessarily. So it's complicated.
And I think at that point we will again mention that it's possible to contribute a different bootloader mechanism here.
Any question about this slide? No? Then I go on. Okay, here are some.
Just one question. So the reference implementation which is right now in the GitHub, the reference implementation for the secure boot. So I believe it's using the secure storage right now for the authentication.
There are components. So secure storage is for runtime, and this is boot time where.
No, but before it puts into the flash, it does an authentication, right?
It do the authentication, but actually the upgrade client functionality doesn't implement it yet. So we have no secure service which are doing the upgrade client. So the starting point that you have a situation when both image is in the flash.
Can maybe cover a little bit more detail of how we have prototypes or timelines, etc. So basically we download the new firmware. So I think what's specific to mention is that basically what we have tried is that we can basically we can abstract out the downloading part of the firmware and do the prototyping of rest, and enable facility where when a client is available, then these hooks can be utilized by that client in creating the whole picture which was present
So
earlier.
you are considering already the image which is downloaded is authenticated. So you're taking it as a, so the image which you have downloaded from the from the server, you think that it is already authenticated?
Yeah, at this stage of the implementation, yes.
Okay, yeah, that was my question.
Okay, this slide is about some device constraint. The header size actually is quite small. It's only around 40 bytes. But it must be placed at the beginning of the image. And there are some certain memory alignment. Then after the header, your image is started and the vector table is there. You need to set the vector table offset register to this certain address. But the vector table register cannot be set to any address in the memory address space. There are some device-specific alignment. So it at least must be these values aligned. So after the header, there is a gap, and only after the image is started. On other constraint is that the two slots, the slot 1 and the slot 0, must be equal size, and the underlying flash layout must be the same. There are some flash which has a homogeneous flash layout, where in that case this is not an issue, but there are some flash where there is inhomogeneous flash layout. In that case, you must be aware that the flash layout must be the same. The scratch size. The scratch area must be at least as big than your biggest erasable unit on the flash. And you must consider that how many upgrades would be possible during the device life cycle. If for any reason you want to upgrade every week, then you probably need to take care about the flash wear out. And you might be better to choose a bigger scratch size, because in that case it's not used so frequently, and you can make a longer lifetime of your device. The image size cannot be as big as the flash area which is allocated for it. We need space from the header, we need space from the image hash value, the digital signature, we need space for the swap status information. So let's say it's around 90% of the flash area can be used for the image, and the rest must be allocated for additional data. Currently, in our version, there is no recovery option. It means that if for any reason the authentication of both images fails, then the MCUBoot won't start anything. And there is no option to use a serial interface to download some recovery image or so on. I know that the original MCUBoot implementation has got this feature recently, but we copied the code before this was implemented. Okay, this slide is about a few threats which can be against an IoT device, and which is more specific on the software upgrade and booting process. A threat can be that a malicious actor tries to send some arbitrary code to your device in order to access the secrets on your device. The mitigation can be to use signed firmware images. In that way, you can be sure that only the code which comes from your server will run on the device. And this is implemented currently in the MCUBoot. It uses the RSA algorithm. Another threat can be that somebody know that there is a vulnerability in your older software version and try to downgrade your device to that version, because he has a ready-made attack vector with which he easily can access to the data. A mitigation can be to use a monotonic counter in your device, which is the image also has the value, and you store somewhere the value in the device, and you compare those values, and if the value is less in the image which is stored in the device, you won't let run those firmware. Currently, we have no implementation against this attack, but we are plan to address this issue. Third can be to install a persistent malware on your device. This can be discovered by an immutable boot code, which is the BL1 image. Our target platforms are not designed to have some immutable code on it. So even there is no flash on the MPS2 development boards, there is only code as ROM. So this is currently not an option for us. Okay, it can be that somebody tries to send an image which has a bug in it, and he wants that your device will fail. It's kind of a denial of service attack. If you have a backup image on your device and you can recognize that the new image doesn't work properly, then you can still do a revert and run the stable version on your device. Currently, this feature is implemented in MCUBoot. It can be that an attacker can access to the private key. If you can access to the private key, he can generate a proper signature which will pass on the authentication, and he can deploy the software on your device. For this reason, it's a good advice that you must ensure that you can replace the keys in the device. If you recognize that somebody stole your key, then immediately you need to install a new public key on the device, and the corresponding private key can be used to sign the new firmwares, and the old private key won't work any further. We want to implement this key revocation and key deployment in the near future. Okay, I mentioned that MCUBoot do the image swapping. Actually, this is quite a complicated logic in the code, and the biggest part of the code beside the crypto library is the image swapping. If your device is a constraint one, that you might be avoid that. So you want to achieve the minimalist code size on your device. So here is some alternative solution when you can avoid to do the image swapping. You can compile a position independent code, which means that any position from the flash you can download your software and will run. Because in a position dependent code you have absolute addresses. When you have a branch instruction, there is an absolute address where to branch. If you have a position independent code, there is no absolute addresses in the code. Instead, you have relative addresses from the PC. So in this case, you can compile the new image, you can run it, you can download it to the slot 1 memory area, and you can start it immediately. You don't need to do the swapping. In this case, the upgrade client must know that which is the currently active area, and it must write the new image to the other area. But there are penalties when you are compiling a position independent code. Your code will be bigger. Might be some libraries can be compiled to be position independent, and so on. But I have a separate slide, the position independent code, because recently we did some experiment on it. Another way to avoid the image swapping can be dual image build. I mean dual image build that you, at build time, you build two binary. One binary for the slot 1 memory area and one binary for the slot 0 memory area. And in this case, you have still the position dependent code. The difference is that is linked to different memory areas. Here, your update client must be clever enough that he recognize which is the active memory area, and he downloads the other binary from the server. And the other binary will be placed to the currently inactive memory area. And this is swapping from boot to boot, which is the active and the inactive memory area. Other alternative solutions can be that if you have enough RAM space, then it doesn't need to run your software from the flash. Running from the RAM is even better. It's faster. You can create position-dependent code, and in this case, you are using the flash just storage place. And the bootloader do the authentication, loads the binary to the RAM, and start it from there. Other solution can be, but as I mentioned, there is no enough RAM in the M-class devices. Usually there is less RAM than flash. This works well with the A-class devices, but doesn't work for the M-class. Another solution can be to have an off-chip storage on your PCB. And this off-chip storage can be used as a storage device. Your update client downloads the new image, and instead putting it to the internal flash, it always copies it to the external storage. And the bootloader, during the boot, authenticate the image, load it from an off-chip storage to the on-chip internal flash, and execute it. But it has some risk, because might be you need to store your firmware in an encrypted form, or might be, Other alternative solution can be that overwrite. I guess David was referring to the overwrite feature when he mentioned that the runtime I/O company doesn't really use the fallback mechanism. So if your device is simple enough, then you can test all the test cases and all the scenarios, and you are self-confident enough that this code will be okay on any devices on the field, then you can do that during the MCUBoot compile time, you can apply a switch which turn on the swapping, and it will turn off the swapping and turn on a functionality which will copy the content of the slot 1 to the slot 0 memory address and do the image upgrade in this way. Okay, this slide is about the position-independent code. We did some experiment on this field. So what we did, we tried to compile the MCUBoot to be position-independent, and tested that can it really run from any space from the memory. We can do that, but there was some issues around it. Might be the most important thing is that the binary will be, I would say, much bigger. So in this size, the 9 kilobyte of increase, it's significant. And it was quite interesting that not really the code of the crypto library or the code of the bootloader itself will be bigger than the compiler for some reason pull in more C library functionalities. It's still under investigation what the reason, because those functionalities was pulled in. there are some limitations around when you try to compile a code to be position independent. It cannot contain any constant pointer. You will get. I did this experiment with the ARM CLang compiler. Might be other compilers behaves in a different way, but ARM CLang has these limitations. If you want to compile a secure binary, there is a special compiler flag which must be applied, but this compiler flag doesn't compatible with the corresponding position independent flag. So actually, your secure binary can't be compiled to be position independent. And there are some other libraries. I tried to replace the standard C library to microlib. My idea was that, okay, here I have a huge increase, replace the library, and might be I can avoid this big increase here. But it turned out, for example, that the microlib library cannot be compiled as a position independent. Or you need to change the library itself. Okay, is there any question around position independent code, or?
Do you plan to support both eventually as an optional config?
It's under discussion. Community can decide. Okay. Yeah, okay. Might be I will skip this slide and go this slide. Asymmetric cryptography can be time consuming. So if you have a device when it's really important that the boot time must be very short, then the asymmetric cryptography is not the best solution because it takes time, especially in a constrained device. So you can do some tricks around it. One trick can be to replace the asymmetric cryptography to symmetric cryptography, or even to hash calculation. This can be done to use the HMAC or the CMAC solution. This works in a way that your upgrade client downloads the image, which still have the digital signature. It uses RSA or ECC to verify the image. And if the verification was passed, then it generates a new digital signature. But those new digital signature is not asymmetric crypto based. This is a HMAC or CMAC message authentication code. But you must be sure, you can be sure that the image is correct because you authenticated it, you create a new signature, and you store both the image and the new signature in the flash. Your bootloader can realize that, okay, I have an additional TLV value at the end of the image, which is HMAC or CMAC. This is depends on the implementation, and can verify that one using hash or asymmetric cryptography, which is less time consuming than the asymmetric version. Other solution can be to speed up the cryptography to use crypto hardware, Accelerator. ARM has an IP, CryptoCell 216, which 312, sorry, which is specially designed for the M-class devices. So it has a low footprint. They actually deliver it with two libraries. There is a boot library, as there is a runtime library. Boot library can be used during bootloader. It can do the signature verification, and it can offload the time-consuming part of the asymmetric calculation from software to the dedicated hardware engine. It supports both the symmetric and asymmetric cryptography algorithm as well. It also contains some nice hardware features. There is a one-time programmable memory. You can provision there your crypto keys, and you can provision there your fallback counters, and so on. This is the plans. They are quite aligned with one slide before where there was about the threats. So we want to support the anti-rollback protection as part of the PSA compliance. We want to create an interface between the bootloader and the runtime firmware. This is need for some features which is recommended by the PSA. For example, the attestation. When your device needs to prove the identity towards a remote server, it's done a way that it tells the server the hash values and the cryptographic signatures of the device. Bootloader has a knowledge and it passes it to the runtime firmware. We want to support chain of trust and key revocation. Also, this is an ongoing how to make bootloader updatable. This is where the position in the independent code is count. And we want to add support to crypto hardware because currently embed TLS is used as a crypto library. But if you have a hardware which has this crypto accelerator, you can switch with a build time switch to use the hardware instead of the software solution. Okay, this is the slide from the previous presentation. Here you found the source code, team members, we are here. There will be an open session tomorrow afternoon. If you have any question, please go there. And basically, that's it. Any question?
I have two questions. Earlier you were saying you try to implement how to revoke the keys if its private key is compromised.
Yeah.
I didn't quite understand. Do you just simply means the ability to update the BL2, or it's something different from that?
If you have a system where you have BL1 and BL2, you can do it in that way that update the BL2. In our system, we have only one BL2. There is no BL1, so we need to find another solution to do the key revocation.
So no detailed solutions to that yet?
No, not yet.
Okay. The second one is we're talking about multiple plans to not to do the swiping, right? Have you considered yet another alternative where basically you keep the update client as an image itself, where you can always revert to that client to do the update? So in case you fail one, you can goes back to the update client image, and then to update the previous one to do the rollback.
So one of the problems in this space is execute in place from Flash. That's third binary you're talking about. Either update client is part of the binary itself or it's another binary, in which case that itself is part of the same equation.
We can talk off the line.
Yeah, okay.
Yep.
So my question is, you called out a method for ATF verifying your bootloader, and a bunch of, I guess, keys and stuff like that goes with it. Is that a standard that you're pushing in the ATF space here? And is it something that should then be replicated in, say, ARM v7, which is something I might be interested in?
Chain of trust is a recommendation by PSA. So you can...
But your specific version, is that standards compliant?
So I think one of the earlier presentations we've covered that this trusted firmware M is supposed to be the reference implementation of PSA. So everything that is here should fall within PSA umbrella, and there is a bootloader part of the specification which will cover what it gets implemented here. What it gets implemented here by our current team, but it may be that people who are using it actually, like for example, you said you may have different requirements. That is why it's an open source project. So it may be that people actually say, well, we need a different mechanism for doing this, and hence it gets maybe implemented and brought into the specification
It's
group.
just
for-
if
for
you guys
consideration.
have already done the work to figure out how to sign stuff, and you have tools for that,
That's
you know,
the MCUBoot project.
you know, we just want to pull that in and.
MCUBoot.org, it already runs on the PC.
Okay, so that's just all part of that already.
So,
you can just take.
so even that, so basically you're talking about the standardization, so even that is a mechanism at the moment. So that's what I'm saying. Basically, whether that's standardized or not is a slightly different question. MCUBoot is a mechanism, and maybe there are others. And platform security architecture might include that, or might say that's not okay. In which
That's very confusing for me.
If you're interested in a standard, there is an IETF working group. So if you're interested in a standard, there's an IETF working group called SUIT, the Software Update for IoT, that is developing a standard for this. But that's an IETF working group. We're quite a ways away from that turning into a standard.
Is that for ATF?
So untrusted firmware for A you're talking, or Vision M?
Well, M would do.
So for M, yes, there is that group, but here, at least in this discussion, we are constraining ourselves to PSA spec. So at least our presentation conforms towards PSA as a set of specifications. So the only recommendation we can give is, if you have a specific requirement, it is better if it's raised to ARM via the PSA program, and that it gets standardized and gets implemented in TFM as a mechanism, or it gets copied or acquired from another place. But eventually what you want is an implementation which actually conforms to a standard that you want to conform to.
I want a shortcut, and if you have something in TFM that we can just take for our V7 project, then that in theory should be fine, right? Because it's already standardized for TFM.
Right. So we, as this has been covered today. So we are at the beginning. So it's not standardized yet. So if you copy today, it's not standardized.
Okay.
The intention is for it to be standardized.
Other question? Okay, if no, then thank you very much.